The wave equation on a wedge. This is problem 1, page 209 in the textbook. Solve the initial dash boundary value problem for vibrations on a wedge. That means we're going to solve equation 1. This is the wave equation in two spatial dimensions where the Laplacian is written in polar coordinates. R runs from 0 to rho, theta between 0 and pi over 2, and t is positive. Here's the picture of this domain. We need to solve this problem. 2 through 4 are boundary conditions. It says that the solution vanishes on the boundary where r equals rho, theta equals 0, and theta equals pi over 2. And equations 5 and 6 are the initial conditions for the problem. The method of solution is, of course, the method of separation of variables, where we'll write our function u of r, theta, and t as the product of r of r times f of theta times t of t, and substitute into the PDE, and we get the equation at the bottom of the slide. The next thing to do is to divide by c squared rft and cancel common factors to get equation 7. Here we have the situation where the left side of equation 7 is a function of t alone, and the right side depends on r and theta alone. And this indicates that both sides must be equal to a common constant, which we'll call lambda, and that gives us the equation at the bottom of the screen. So this gives us actually two equations. Equation 8, t double prime plus c squared lambda t, that's the t equation, which we'll solve later on, and the equation at the bottom of the screen. So this equation, what we're going to do is move the minus lambda term to the right-hand side and move the f double prime over f with the 1 over r squared factor to the left, and then afterwards multiply both sides by r squared. When we do that, we get equation at the middle of the page here, and we have again a situation where one side depends on one variable. The left is a function of theta alone, the right is a function of r alone, so both sides must be equal to a constant, which we'll call mu. And so the left side gives us the equation 9, f double prime plus mu f equals 0, a standard equation we've solved many times this semester. And the right-hand side gives us equation, when it's unraveled, equation 10, which we recognize as Bessel's equation of order mu. We next apply the boundary conditions, and let's go through them. The boundary conditions are given above in equation 2 through 4 translate as follows. That the solution should be bounded as r goes to 0 from the positive side translates to r of r bounded as r goes to 0 from the positive side. The condition that the solution vanish when r equals rho on the boundary of the wedge translates to r of rho equals 0. And similarly, the two conditions specified in the last two lines tell us that f should vanish when theta equals 0, and it should vanish on the boundary when theta equals pi over 2. So we have two eigenvalue problems plus the t equation. Here's the first one. This is f double prime plus mu f equals 0, and the two boundary conditions. This is a regular Sturm-Liouville problem that we've solved multiple times this semester. The second equation is the radial equation, and the equation is Bessel's equation of order mu with the two boundary conditions that the solution should vanish when r equals rho, and the solution needs to be bounded as r goes to 0 through positive numbers. So we have 11 and 12, the two eigenvalue problems, and equation 13, which we'll determine after we know lambda. The eigenvalues and the eigenfunctions. Let's solve these two eigenvalue problems. The first one, the f equation, is a standard equation that we've studied multiple times this semester. Its eigenvalues are given by n pi over 2, that's n pi over L, quantity squared, which works out to be 4n squared, and the eigenfunctions are non-zero multiples of sine 2n theta. Next, the r equation. Using mu now equals 2n squared, substituting into equation 12, we get the equation in the middle of the page here. This is Bessel's equation now of order 2n. From our study of Bessel's equation earlier in the semester, we know that the bounded solutions of Bessel's equation of order 2n are given by the Bessel functions j of the first kind. So R of R, the bounded solution, is going to be j sub 2n with arguments square root of lambda times R. Applying the boundary condition R of rho equals 0, we obtain the condition j sub 2n evaluated at the square root of lambda rho equals 0. Now, it's standard notation to denote by z sub nm the mth positive root of Bessel function j sub n, where n in this case starts at 1. For our problem, when mu sub n equals 2n quantity squared, we have to use the notation z sub parenthesis 2nm to denote the mth positive root of the Bessel function j sub 2n. So we can solve the previous equation by setting the square root of lambda sub nm rho equal to z sub 2nm. We need to put double subscript on lambda because z has double subscripts. Hence, the eigenvalues, lambda nm, are given in equation 14 here in terms of the z's, and the eigenfunctions r sub 2nm are given in terms of the Bessel functions. Finally, we need to solve the t equation. Now that we know that lambda, the eigenvalues, are all positive, we know the general solution of the t equation in terms of sines and cosines is given in equation 15. So, since we know the solution of the r, t, and f equations, we can write down the general solution. It's a product of the r equation, the Bessel function j sub 2n with its argument, the theta equation, the eigenfunction sine 2n theta, and then finally in the last factor in equation 16 contains the solutions of the t equation. We're going to need u sub t for the second initial condition, so I've written it down here in equation 17. Let's now apply the initial condition u of r theta at t equals 0 should be given by the function, the initial shape function f of r theta. So when we evaluate equation 16 at t equals 0, we get equation 18. I have a remark about the Bessel functions here. We want to, of course, use orthogonality to solve for the coefficients, but we've got to remember that the orthogonality relationships for Bessel function involves eigenfunctions with a fixed value of n. In fact, the formula is given here in equation 19. You'll notice the subscript on both j's is the same. This is the orthogonality relationship for the Bessel functions. So the conclusion is to solve for the coefficients in 18, we need to fix the value of the index n on the Bessel functions. Then we can use formula 19 to find the coefficients. So view equation 18 above. I see it says view 0.05, which should really be 18, as f of r theta, where we have what's in the box, we view it as the coefficient for this Fourier sine series expansion. So thinking of r as fixed, we can use the orthogonality of the function sine 2n theta to solve for what's in the box. And we get equation 20. Now, we want to view this equation as follows. Since theta is integrated out in the above equation, the left-hand side is a function of r alone. Hence, this equation is the orthogonal expansion of this function in terms of the complete orthogonal family of eigenfunctions in terms of the Bessel functions j sub 2n. Hence, we may use our orthogonality relation 19. Do the following. Fix a positive integer k and multiply both sides of equation 20. Now let me remind you, here's equation 20. Both sides by r j sub 2n of its argument and integrate from 0 to rho. And it gives us the equation at the bottom of the screen. The right-hand side collapses to the single term in the sum when m equals k. We know that the eigenfunctions are orthogonal. So it reduces down to this this formula on the right hand side, it's the integral from 0 to rho of r of the square of the Bessel function j sub 2n, where our k, index k on the eigenvalue lambda. We can solve this equation for alpha sub nk, and I'm going to relabel it as alpha sub nm, by dividing both sides by the integral on the right. Next, applying the initial condition 6, namely the t partial derivative of the solution function should vanish at 0, we have equation 22. A careful rethinking of how we pass from equation 18 to the result given in 21 for alpha sub nm once led to the conclusion that beta sub mm is given by a similar formula, except now we're integrating 0 in the numerator and we have this extra factor of c times the square root of lambda nm in the denominator. But a definite integral of 0 is 0, and hence all the beta sub nm's vanish. Here's a summary then. The first line is the general solution of the equation of the initial dash boundary value problem, and the coefficients are given in the formulas at the bottom of the screen.